Hi, my name is Katherine Jijo, and I'm a machine learning engineer intern here at Anno. My team and I worked on a research project regarding the cutting-edge advancements in leveraging few-shot learning, fine-tuning, and active learning methods to enhance the accuracy of large language models such as GPT, BERT, and CEPHIT. Today, we'll be going over how these methodologies, coupled with continuous human feedback, increase model accuracy, recall, and precision amidst the challenge of limited labeled data. So let's start off with a quick dive into the history of LMs. For example, BERT, Claude, and Cephit are transformers that are all pre-trained on various datasets regarding things like mathematics and history. But due to the fact that they're pre-trained on previous datasets, they can tend to hallucinate or fabricate responses when faced with unseen data. Fast forward to now, we have developed these things called machine learning paradigms, which are methods that serve as foundational concepts that help guide the design and implementation of algorithms across various domains like reinforcement learning or supervised learning, as well as newer techniques that can increase the accuracy of these LMs, such as active learning, few-shot learning, or retrieval augmented generation. Our mission is to explore how few-shot learning, fine-tuning, and active learning methods can significantly increase the accuracy of LLMs like GPT, BERT, and Cephit. In the challenging landscape of AI and ML, where obtaining sufficient labeled data remains a challenge, particularly for unstructured text, our focus lies in leveraging a continuous human feedback loop. This iterative process aims to fine-tune models and elevate their accuracy, recall, and precision, all while operating within the constraints of a limited number of labeled examples. Our results speak for themselves, showcasing a consistent improvement in accuracy across domains of various datasets. These findings underscore the transformative potential of few-shot learning and active learning methodologies, enabling us to refine LMs efficiently with minimal labeled data and human feedback. We benchmarked multiple datasets to explore different domain applications. One is an Amazon dataset, which had class labels such as excellent, very good, and bad corresponding to customer reviews. Another is the financial phrase bank with phrases like positive, negative, and neutral as labels, which correspond to the direction of financial markets. Currently, we have zero-shot models, so think of a baseline large language model like GPT, pre-trained on various domains that are not made to be successful in text classification tasks. Our methodology capitalizes on few-shot learning techniques to enhance the classification with minimal labeled data examples. We begin our classification process by identifying potential areas where initial model predictions may be inaccurate, and an integral part of our approach entails iterative refinement through human feedback. By continually integrating human input, particularly in the earlier stages, we empower the model to improve its predictions. In Table 3, regarding a spam prediction use case, the model initially struggles with the classification task. Our process facilitated by providing human feedback of providing a label, the model gradually increases its predictive accuracy. Now the model is able to predict not spam label as the correct answer of spam, leading to enhanced performance. Another solution for increasing the accuracy of zero-shot models is fine-tuning with human feedback. For our use case, we can look at stock market sentiment. The market has a need for a concise response to sentiment analysis, and this necessitates a solution that can deliver accurate outcomes without the unnecessary complexity in wording or length. Let's say you call the OpenAI API key and you ask a question about market sentiment. Despite GPT 3.5's capabilities, the challenges still persist where lengthy predictions or explanations are provided by the model, especially when a simpler format is desired, and this is harder to retrieve insights from as well as calculate accuracy scores. To address these challenges, our solution centers on the iterative refinement process with human feedback, so we systematically fine-tune the model by incorporating 10 rows of data at each iteration, and each row has the correct answer as well as show the model the desired response format. However, we do have to add and acknowledge the limitation that the model does tend to hallucinate even beyond what is prompted. Let's talk more about few-shot learning. Traditional AI approaches heavily rely on training models with extensive data sets containing millions of rows, and this involves associating inputs such as images or text with accurate labels. It involves providing the model with only a few labeled examples iteratively to provide higher accuracy. And just to show how great our methodologies are, let's take a look at these accuracy graphs. Zero shot without feedback, we can see that the accuracy is stagnant and the line is horizontal because there's no intervention. But the graph documenting our few-shot approach shows that the more shots or examples given by the human, the more accurate the model can become. Now let's look at the accuracy, recall, and precision graphs for our Amazon dataset. You can see that as we increment 10 rows of labeled examples at a time and 150 rows, all of our evaluation metrics increase. Let's talk about why this is important. The ability to classify text data effectively translates to great business benefits by enhancing decision-making processes and improving operational efficiency. In the healthcare sector, text classification enables the categorization of analyses of patient records, medical reports, and research articles. And similarly, in the finance sector, by accurately categorizing financial documents, news articles, transactional records, organizations can identify risks, anticipate market trends, and make informed decisions. In terms of our next steps, our plan is to continue benchmarking and refining these models with feedback. And in summary, we recognize that large language models accuracy will only get better. However, we need to leverage things like fine-tuning, few-shot learning, and active learning to increase the accuracy or apply them to domain-specific use cases. You can access our code or research paper on this topic on the NL website. Thank you.